Okay, welcome back to our statistics class notes. Our Calculus 3 class notes. We are still in section 14.6, and now we're looking at the plane tangent to a surface, z equals f of xy. So what page? We're on page 63 here of your notes. So if you remember on the previous page, if we had a surface, right here, if we have a surface that is thought of as a level surface, f of x, y, z equals c, then this is the equation for a plane through p naught normal to the gradient of f. So if we just look at any surface, z equals f of x, y, the best way to think of this to follow that same equation is to think of z equals f of x, y as f of x, y minus z equals 0. So that would mean that the piece over here that is the partial of f with respect to z will just be minus 1. But then this is the same f sub x and this is the same f sub y, so the equation is the same. It's just that we now know that our partial of f with respect to z is only minus 1. So if I want to find the plane tangent to the surface, z equals x cosine y minus y e to the x, I just find my gradient of that f, which is f sub x and f sub y. I don't need to think of this by subtracting z and setting equal to 0. I just know that I will always make this piece of the equation a negative 1. So I just look at the gradient of f, which is f sub x and f sub y. So that's going to be cosine y minus y e to the x, looking at this up here. And partial of f with respect to y is going to be minus x sine y minus e to the x. So evaluating that at 0, 0, I get 1 minus 1. So that means it's 1 times x minus 0 minus 1 times y minus 0 minus 1, which is, I know that will always be the case of that being a minus 1, times z minus 0 equals 0. So that's just x minus y minus z equals 0. All right, let's make it a little bit more complicated here in example 58. Let's say we have the surface is f of x, y, z equals x squared plus y squared minus 2 equals 0. That's a cylinder. And g of x, y, z is x plus z minus 4 equals 0. That's a plane. And you can see I tried to draw it here. If you cut a plane at an angle through that cylinder, that circular cylinder with the radius of square root of 2, right? Then it's going to cut it in an ellipse. So we want to find parametric equations for the line tangent to this ellipse at the point P naught 113. That's this point on the surface right here. We want to find the tangent line to that ellipse. So the tangent line is orthogonal to both the gradient of f, right? Because the gradient of f is going to be orthogonal, and if you think of that cylinder as a level surface, then gradient of f is orthogonal to the cylinder, and the gradient of g is orthogonal to the plane. So what happens is that the tangent line is orthogonal to both. So the gradient of f at P naught and the gradient of g at P naught is what we need to look at. And I get the gradient of f and the gradient of g, evaluate them at P naught, which is 113, and I get these two vectors. So a vector that is parallel to the line is going to be orthogonal to both the gradient of f and the gradient of g. So I know I can find a vector parallel to the line by crossing those two vectors. So that means that the vector v, which would be parallel to the line, is the cross product of the gradient of f at P naught with the gradient of g at P naught. And you work that out and you get that's 2 minus 2 minus 2. So that's our vector that's parallel to the line, which is the coordinates, the coefficients of t for each component of the parametric equations. So, and then the vector, or the point that's on the line is the one that's given, the point 113. So x equals x naught plus v1t is x equals 1 plus 2t, and y equals y naught plus v2t is 1 minus 2t, and z equals z naught plus v3t is going to be 3 minus 2t.